Hey folks, today we're talking about acids, bases, and salts. We are starting an entirely new unit, so we're going to do the introduction. Make sure you're ready to take some notes on this unit. We've got a lot of terms you're going to be seeing. Some of this you should have seen before. Some of this you should already be familiar with, but just make sure you get it all. Okay? First thing we're going to talk about are acids. Acids are everywhere around us. We see them every day. A perfect example would be a bottle of Dr. Pepper. I know it's gross, but guys, when you vomit, that's exactly what gastric acid is. Gastric juices are acidic, and in fact, they are exactly the same stuff that you will find in pool acid. Pool acid, these are both hydrochloric acid. Both gastric juices and muriatic acid or pool acid. And then, of course, you've got vinegar. We've talked about that before. That's acetic acid, which looks like that, HC2H3O2. All right. Now, we do have lots of acids around us in other things. For example, over here we've got a lot of citric acid. In lemons and limes and grapefruits and oranges, they all contain citric acid. And down here, these are warheads, which if you've ever had them and you look carefully at one of these warheads down here, they have a white coating on them. And the white coating is ascorbic acid. And ascorbic acid is actually vitamin C, which of course is also in citrus fruits. So it is just coated with that white stuff that's on the outside that makes them really, really sour when you first put it in your mouth. That's ascorbic acid, so it is an acid, so it tastes very sour. And so that's how you know that acids are sour. Okay. Coffee and tea are both acidic, so that's an example. Coffee has about 8 different acids in it. The main acid in tea is called tannic acid. So again, we have lots of acids around us. So soda is acidic, and you say, really? It's really acidic? Well, yeah, it is. When you look at Sprite, Sprite is going to contain citric acid, just like lemons do. And if you look over here, you will see that Sprite contains citric acid. And you say, well, wait a minute. Sprite isn't sour. Well, the reason it isn't sour, or actually the reason it doesn't taste sour, is you've got this high fructose corn syrup in here, which makes it very, very sweet. So when you look at Coca-Cola, for example, Coca-Cola is mainly carbonated water, and its second most popular ingredient is high fructose corn syrup. But if you go further down, you're going to see phosphoric acid. So Coca-Cola does contain, again, an acid. All right. When you have acids and you touch them, so long as they're dilute, we're not talking about strong battery acid here, but so long as you touch something like grapefruits or something and you get some of the grapefruit juice on your skin, assuming you do not have any cuts on your skin, then it's going to feel just like water. You really can't tell the difference between water and grapefruit juice. Now, of course, you wait a minute, you say, well, when it dries, yeah, you can. But just as a liquid and it's dilute acid, you can't tell. Now, of course, if you do have cuts on your hand, it's going to sting because it is acidic, and it's going to sting in those cuts, and it's going to hit the nerves, and that's going to hurt. Right? Acids are also corrosive. They react with metals. So if you get battery acid on something, it's going to corrode it on a metal. This is an example over here of acid rain hitting your car. If you have a car that is not protected well by wax or by some polymer, you end up with some serious battery acid, some serious acid rain damage to your car. Right? Tomato juice. Tomatoes are an example of something that is acidic. If you look at the inside of a can of tomatoes, you'll notice that it's coated in a white substance. And the reason is that the tomato, the juice of the tomato, because it's so acidic, will actually go and it will start to dissolve the inside of the can. So they coat these cans with this white substance, this white plastic substance, to protect the can. Right? So that's what happens with acids. Now, acids can also react with things like your teeth, which I'm not going to show you a picture of tooth decay. I thought about that and just said, no, that's really nasty. But also, here's a statue of George Washington. He's seen better days. Again, the acid rain is corroding the concrete. So acids are all around us, and they can really affect the things that are around us. Now, you also know that acids are strong, that like HCl is a strong electrolyte. We talked about that in a previous podcast. If you remember this gentleman over here who did a demonstration for you with the difference between a strong electrolyte and a weak electrolyte. And acids are electrolytes, and depending upon whether they are strong or weak, the strong ones conduct electricity really well, and the weak ones only conduct it a little bit. All right, let's switch gears and go over to bases. Bases are things like soap, and they have a bitter taste to them. Okay, so if you've ever tasted soap, you know that it has a really, really bitter taste. Now, most most bases we don't eat. There's very, very little that we eat that's basic. When you think of some of the bases that are around us, if you get bleach on your hands, it feels very slippery, or Tilex, which includes bleach, is very slippery, or some Easy Off oven cleaner. This contains NaOH, sodium hydroxide, and it is very caustic, and it's very poisonous. And you want to, if you get that on you, it's going to feel very, very, very slippery. All right. Now, they don't react with metals. So, and that makes sense, because if they did react with metals, then you couldn't put Drano in your drains, because it would eat the drain away. But they don't react with metals, but they do react with other things. Again, you couldn't use Easy Off oven cleaner on the inside of your oven if it was going to destroy the inside of your oven. Okay. Many bases are poisonous. In fact, most are. So there's very little that we eat that is a base. Again, bases are, if they're strong bases, they're going to be strong electrolytes. If they're weak bases, they're going to be weak electrolytes. But in either case, they are electrolytes, and they do conduct electricity. And remember, the reason for that is that bases and acids will dissociate into ions. And when you have free ions in the water, they will conduct electricity. All right. We do have litmus paper. Litmus paper, we have blue litmus paper. This is blue litmus paper up here. And if you get a drop of acid on blue litmus paper, it will turn the paper red. Similarly, this is red litmus paper. If you get a drop of base on a red litmus paper, it'll turn blue. Now, if you were to get acid on red litmus paper, nothing happens. If you get a base on blue litmus paper, nothing happens. Okay? But if you get acid on red litmus paper, on blue litmus paper, it'll turn it red like you see here. Okay? So we have a lot of ways to determine if something is an acid or a base. So if we have a liquid and we just want to try a drop of it on something, this will tell us whether it's an acid or a base. If we happen to have some phenolphthalein indicator, then phenolphthalein in an acid would be clear. You'd see no color at all, but in a base, you'd see pink. And you're going to see that in a future podcast when we actually do something called a titration. Right, but that is another acid-base indicator, and all it does is indicate whether it's an acid or a base. It doesn't tell you how acidic or how basic it is. But we do have some universal pH paper, and you'll notice over here your pH of 1 and 2 is very red, and your pH of 13 and 14 gets to be blue and almost purple. This paper will change color based upon whatever you put on it. And 7, by the way, is neutral. If you don't remember that, we're going to talk about that more. 7 is neutral. So that's universal pH paper. So again, you have a liquid, you can put a drop on it and see what color you get. Right? Now, we also have universal indicator. You're going to see this in a future podcast as well, where if you take some drops of universal indicator and you put it in liquid, depending upon how acidic, these are all acidic over here. These are all acidic. And over here, these are all basic. And the one in the middle is neutral. So you will see, again, in a podcast in the future, that we can have some neutral, some water, for example, which is neutral, and it'll turn green with an acid-base indicator. But if you have an acid, it turns yellow and then turns red, and if you have a base, it turns blue. All right, we're going to do some neutralization with some titrations. You'll see that, again, in a lab we're going to do. An acid clearly will neutralize a base, and a base will neutralize an acid. However, they have to be in the right proportion to do that. And that's important. You can't just throw some acid in the base and say, oh, it's neutralized. Well, no, it's not. Did you add enough? Did you add too much? Well, it has to be just in the right proportions to make it come out to be neutral. Right? And based upon what I'm seeing down here, I'm guessing, since that's yellow, that is slightly acidic. How would I guess that? Well, look right there. There's my yellow over here. So I'm guessing that is slightly acidic. All right. So let's get into some definitions of what acids are. There was a Swiss chemist named Arrhenius, and he came up with the concept of an acid and a base. And he said acids and base could be understood in terms of ions they release when dissolved in water. Notice it is in water, so write that down. The Arrhenius definition is a great definition, but it has to be in water. All right, so acids when they break apart in water, they produce hydrogen ions. Now, you will often see us use just H plus ions for hydrogen ions, all right? But also, because it's in water, what happens is when you take an H plus ion and you add it to water, you end up often getting a hydronium ion, which is H3O plus. So actually, that oxygen, which normally just has a hydrogen over here and has a hydrogen over here, and remember it has two pairs of free electrons over here, what happens is that that H plus ion will come over here next to these two electrons, because these two electrons are negative, and it will create a bond here. So you end up with 3 hydrogens coming off this one oxygen. But that means this entire thing has a plus charge. Okay. Now, a base will dissociate in water to produce hydroxide ions. So think of what water is made up of. Water is made up of H and OH. We sometimes write it that way, especially when we're balancing equations. So if you have an H and an OH, when they split apart, you get an H plus and an OH minus. So the H plus is the acidic part, and the OH minus is the basic part. And that was the Arrhenius definition. So if you look at all of these acids over here on the left, they all start with an H. Now, you might want to pause the video and see how many of these you can name. You should be able to name all of them. They're all reasonably common. So go ahead and pause the video, see if you can name them. All right, did you really do that? Well, let me just go through them really quickly. That's hydrochloric, that's nitric, that's acetic, sulfuric, carbonic, phosphoric, hydroiodic, iodic, iodic, right, and hydrobromic and hydrofluoric. Now, all of your bases are real easy to name because these OH things, they're all hydroxides. So your first one would be sodium hydroxide. Can you name the rest? Pause the video, see if you can do that. All right, sodium hydroxide, potassium hydroxide, magnesium hydroxide, calcium hydroxide, and barium hydroxide. Why do we have these 2's out here? Well, the 2's come because magnesium has a 2 plus charge, calcium has a 2 plus charge, and barium has a 2 plus charge, and the OH's all have a minus 1. All right. Acids and bases could only be understood when they are in water. So what is HCl as a gas? Well, when it's in water, you call it hydrochloric acid, but when it's a gas, you just call it hydrogen chloride gas. The same thing is true for hydrosulfuric acid when it is dissolved in water, but as a gas it would be hydrogen sulfide. All right, let's quickly look at a neutralization. Acid-base neutralization always produces an ionic compound, which is called a salt, and water. Now, a salt is any ionic compound. So we tend to think of salt as being NaCl. So if we take hydrochloric acid dissolved in water and sodium hydroxide dissolved in water, they produce more water and they produce salt, NaCl. So literally what we do is we're taking vomit, for example, gastric acid, or we're taking pool acid, hydrochloric acid, and we're mixing it with sodium hydroxide, which is the stuff in Drano. And both of these are extremely dangerous stuff, but we mix them together and we get salt water. Wow, that's pretty cool. And we're actually going to do that in a demo in a little while, but I wanted to let you know that's what we're producing. We're producing salt water. It's a double replacement reaction. And often, to make this a little bit clearer, we write the H2O as HOH. So you'll notice the H is coming over with the OH to make HOH, which leaves the potassium and the bromine to come together to make potassium bromide over here. Now, of course, we're making water, which is a liquid, and then the potassium bromide is dissolved in water still, so that's called aqueous. All right, a couple of more. It's important to realize that what we're doing is any of these things, we're always producing water, which is here, and we're producing KNO3, which is considered a salt. The same thing here for calcium iodide, it's considered a salt. Now, to balance the reaction, we've got to put 2's over here. I mean, you can balance reactions. You guys know how to do that. But just want to make sure that you see a couple of neutralization reactions. All right, just a reminder on your acid naming rules. You haven't done these in a while. Remember, if your anion ends in IDE, then it's a hydroic acid. ATE, it's an ic acid. And ITE, it's an OUS acid. If you haven't memorized that, please write it down and memorize it, because you should be able to name acids pretty easily. Again, looking at these, pause the video And please try and name these. If you need to, go back to the previous slide for your naming rules, and then write them down. All right. Guys, as you've been finding as you're taking tests, if you can name things quickly and you can come up with the right formulas, then it's real easy to take a test. If you can't, that's going to really slow you down. Okay, so this one is hydrochloric acid. This one is chloric acid and chlorous acid. And it's hydrochloric because this is chloride, so it's hydrochloric. This is chlorate, so this becomes chloric acid. And this is chlorous, so it becomes, this is chlorite, so it becomes chlorous acid. Okay. Your bottom ones here, this is hydrosulfuric, sulfuric, and sulfurous. All right, let's go do it the other way. Pause the video, see if you can do these. Phosphoric acid means you're looking for a phosphate, which is PO4. All acids start with H, and because phosphate takes on a 3- charge, you have to have 3 hydrogens to offset it. Hydrophosphoric acid means you're looking for a phosphide, which is P. And again, all acids start with H. P takes on a -3 charge, so I need 3 hydrogens to offset it. How about phosphorus? Phosphorus means I'm looking for phosphite, which is PO3. All acids start with H. Again, phosphite takes on a -3 charge. I need 3 hydrogens to offset it and balance it. Okay, we have 3 types of, again, terms. You need to write these down, so pause the video and write them down. You have something called a monoprotic acid, mono meaning 1, and you'll notice there's 1 hydrogen. A diprotic acid, meaning that it releases 2 hydrogens, and a triprotic acid, meaning it releases 3 hydrogens. Now don't be confused, these are the hydrogens that are available for to separate and become an acid. So when we write, for example, acetic acid, HC2H3O2, you say, well, this has 4 hydrogens. Yeah, it does, but only one of them, this one here, breaks apart. So this is going to be a monoprotic acid as well, because this would break up into H positive and C2H3O2 with a -1. That's an acetate ion. Okay, so this is acetic acid, acetate ion, but only 1 hydrogen is available to break away, so it's considered a monoprotic acid. All right, now there are some problems with the Arrhenius definition. The biggest problem is the Arrhenius definition says acids and bases need to be dissolved in water, so we can only have liquid solutions. That's too simplistic a definition because there are some other compounds that have characteristic properties, specifically of bases, that cannot be included unless the OH-1 ion is present. Okay, so for example, NH3 is an example of one of these bases, and you'll say, well, wait a minute, NH3 does not have an OH anywhere. All right, so there were a couple of other guys, Bronsted and Lowry, who both came up with the same definition at essentially the same time, and they said that an acid is any substance that can donate hydrogen ions, and we call them proton donors, is they can give up a hydrogen ion. So for example, if you had something like HCl, HCl is going to give up a hydrogen ion. All right, it's going to give you a hydrogen ion. And a base is any substance that can accept a hydrogen ion, so they become proton acceptors. So these create many more compounds that act as bases that can accept hydrogen ions. Now remember, what's a hydrogen ion? A hydrogen ion is simply a proton, because a hydrogen is typically 1 proton and 1 electron, but there are no electrons when it's positive, which means all you have left is a proton, and that's why we call it a proton donor. All right, so we have some other bases, things like ammonia, baking soda. Baking soda is NaHCO3. We have Tums, which is calcium carbonate, CaCO3. All right, so you don't see OHs here, but they still act as bases. I'll go into that a little bit more in the next podcast. All right, I think that's it. Have a great day. Sorry that was so long, but we had a lot of material to cover. And enjoy your afternoon. Enjoy your day. We'll see you later. Ask us if you have questions in class. Take care. Bye.